So can you please go to the next slide? Yeah, this is just a overall view that when you want to study at larger scale, then you want to have this earth and the space, and smaller scale is 10 to the plus 9, 10 to the minus 9. Next one. Next. Yeah, for studying at larger scale, you have to send an agent to their outer space, and for go next, you keep on going to the next one. And then for a smaller scale, you have to send some other agent, that is either ion or electron or something to the, so it's 10 to the plus 9 to 10 to the minus 9 scale. Next. So some typical energies are these, that you have electron volt and whatever 1 to 20 kV for the screen and ionization and so on. Next. Next. Okay, to have the agent, to have some energy, you need the accelerators, and that we have enough accelerators in the country now. One is at IUC Delhi, and then there is a TFR Bombay, and many accelerators are there. So once you want to do that, then you have to accelerate your particle and then send these particles to the what you want to study. Okay, next. That is also a part of accelerator. Next. This Van de Graaff picture, and next. Yeah, here is that charge goes from one side to the other. Next. Here is the accelerator from you see the BRC TFR, and then similar is the one for the IUC Delhi. Next. This Pelotron in Delhi, IAC Pelotron Inter-University Accelerator Center. Next. So here the linear accelerators, the thing is that you have to, when particle goes from one place to the other one, then you have to do the proper tuning, so that when by the time particle goes to the next, the polarity changes, and that's how the linear accelerator works. Next. Yeah, so that, for example, the SHI1 has gone from that much distance, has to be properly tuned, so that by the time it goes to the next, the polarity has changed. Okay, next. That's the principle of linear accelerator. Next. So applications of the proton therapy and so on, actually in Denmark and UK, in Germany, they have started using these things for the cancer treatment, and in Darmstadt they have been using that. Next. So motivation of this is that ion beam processing, you can, what is the important thing is that you can change the material at your wish, and you can change from whatever want to, and most importantly, the spatial accuracy. You can change at one place something and another place another thing. So on a single chip, you can have many chips. Okay, next. So nanomaterials, there are two ways, that is bottom up and top down. This is atomic energy levels. Next. So bottom up is the going from depositing materials from one atom to another, and top down is cutting and polishing. In each case, you have to go to the nanometer scale, and then the scale. From bottom up, starting from an atom, and top down is starting from a bulk material. Next. And in this case, for example, so this is your atom, and this is your bulk. Okay, this is your bulk and this is your atom. So in each case, you have to go from here to here. That is here. From by putting more atoms, you go to the quantum dot, and from here cutting parts, you go to quantum dot. In each case, energy, what is important is the energy band gap. Energy band gap in the energy level here, that has to be controlled by the size of the material. Okay. So size of material here, next slide shows that. Next one. So in that case, what you have to do is that your this Bohr exciton diameter has to be of the order of the size of material, and in that case, energy level becomes dependent on the this dimension of the material. Next. Yeah, for example, energy level, the energy band gap depends on the bulk plus K by D. So D is the small, D is the size. So D is small, then you can go to the bulk, the energy band gap can become more. If D is 0, then it becomes infinity, but if D is very large, then it is bulk. So if d is of the order of a few nanometers, then the energy of the quantum dot becomes more than the energy band gap of the bulk. That is next. And these are the synthesis methods: atom beam sputtering, magnetron sputtering, and implantation. For synthesizing these material, and then post deposition treatment, you have to do all these things. Rapid thermal engineering, but I will talk most about the next one. Next. See, atom beam sputtering, you have to, in that material, you have to send the metals, and then it deposits whatever you want to deposit on the substrate. You have to have these chips of that, and then by 1.5 kV atom energy, then you can deposit it. Next. And then after you have deposit, then you have to characterize various characteristics, whether foldback scattering, X-ray diffraction, Raman spectroscopy, all these things. But finally, you have to do the TM, transmission electron microscopy, so that you have most accurate method of characterization. Next. So basics of ion-solid interaction I will quickly go through, but that is when a particle is sent into the material, then this particle loses energy to the electron of the material, that is electron gas of the material, and also to the nuclear, that is the atoms of the material. Energy laws, the mechanism of solid interaction. Next one. So electronic stopping, and this nuclear stopping is a misnomer. Actually, it is nothing to do with the nucleus. It is actually the radiation damage. Electronic stopping, these are the processes which take place, and this is the nuclear stopping where radiation damage takes place, damage of the material. Nuclear stopping is a misnomer, as I said. Next one. So by electronic stopping, if the particle is going very high velocity, then it is somewhere at the end of this velocity, this T by dx works velocity. So high velocity, it is mostly the electronic stopping, and then it goes through initially and then comes down to the nuclear stopping, that is radiation damage. Next one. This is nuclear energy. Nuclear, again, I said misnomer. It is actually nothing to do with the nucleus. It is atomic displacement. Okay, so when the particle comes, it displaces the material, and then you get the nuclear energy, nuclear stopping. Next one. Here. So the d by dx versus the velocity. At high velocity, it is mostly electronic stopping, and then it comes to the lower one, then you get SN nuclear stopping or atomic radiation damage part of it. So electronic stopping is in somewhere in this region, and that is where what you want to, when you want to do the material catalysis, material analysis regime, then you have to, in this region, material modification. Material analysis means it has to be somewhere in the, purely in the electronic region, and material modification means it has to be in the nuclear stopping region. So depending on what you want to do, you have to change your energy. Next. Now there is this important aspect of this, that is when you are sending the particle to the material, then its crystalline structure becomes important as soon as the particle goes along one of the directions, that's called process of sending. So for example, this is the backscattering, Rutherford backscattering thing, even RBS yield. And as you go to the more and more energy, then there are these things. But as soon as you, next one, next. So as soon as you go along a small direction, very small angle with respect to the crystallographic direction, then what is called ion channeling takes place. So particle coming with this at a small angle, and that angle has to be small of 1 degree or less. That depends on the energy of the material. Next. So that energy of the material, next one, that energy of the material, that depends on the particle, the potential has to be calculated. Next one. So critical angle is that Z1 is the projectile charge, Z2 is the target charge, and D is the interatomic distance along the direction. So if the Z1 and Z2 are small, then Z1 is the projectile charge. For example, Z1 is 1 for the proton, and Z2 is the silicon less 14. So that's what decides what is the critical angle. Critical angle, by critical angle, I mean that for angle less than that, it will just go, channeling will take place. Next one. And when that happens, that for high energy, for example, radiation takes place, it's called channeling radiation. There are two aspects: at lower energy, you can do the analysis, and at higher energy, you can have channeling radiation. But here, the angle has to be very small. Next one. For example, when you are count that is photon yield versus of the photon energy in keV, then at certain angle, at certain energies, it is very high. Okay, for example, here. So that is, for example, radiation from gamma is going to 7, that is 53 MeV proton, very high energy. Relativistic, this happens with relativistic energy. Relativistic energy, a new kind of radiation which I just now showed the previous slide is changing radiation. The next one, and this is for electron, for plasma or proton, this is for electron. For electron, many peaks are happening. The proton goes through, proton or positively charged particle will go through, electron will go through along the direction, whereas this electron will go along the, it will be having this attractive attraction with the ion, so it will weave around that. So that is why there are so many. Next one, here. To left frame, then Pakistan is going, then it is moving into the between two planes, whereas the electron goes, then it will move along, weave around that. So the energy law, this is the particle is confined into the transverse direction, and potential is then because the confinement, their energy levels are discrete, and that transition among the energy levels gives rise to the radiation, changing radiation. And that radiation, when you go from left frame to right frame, then the factor of gamma is 100 for the 50 MeV positons. So then that means this energy level becomes more. Next one. And once that is happened, then we are observing the left frame. From right frame to left frame, we have to go again. So that gamma becomes 2 gamma square because Doppler effect takes place. Initially, it is the Doppler effect and then relativistic effect of the radiation. By whatever has been there, then it will be having gamma 2 gamma times per factor, because then you are observing in the left frame from rest frame. Rest frame, this is the rest frame energy. When that has become gamma because of the Doppler effect, and then because of the relativistic effect, and Doppler effect gives the 2 gamma factor. So the energy of this radiation becomes very high keV as compared to Bremsstrahlung 1. Bremsstrahlung 1 is only electron volt region, but it is to keV region. So that's why this is a unique radiation, and this radiation is the monochromatic. Next one. So at lower energy, for example, the stopping power which you talk electronic stopping power, this is oscillations, silicon 110. Next one. For gold 110, then next one. Next. So the to understand that, one has to do that when the charge particle is moving in the between the channeling along the crystallographic direction, then electrons which are scattered from there to take away the energy, and that energy taken is given by this formula. NMB square, N is the density of the electrons, and QD is the transport momentum transfer cross section. Momentum transfer cross section depends on the phase shift of the scattering. As the next one. So this is the standard equation, the radial part of the equation, that k square plus ur minus L. So effective potential is ur, that is the potential due to the particles, due to the ions, and then the potential of the moving ion, and this is the centrifugal force. So this is minus ur plus L. So next one. Yeah. Effective potential, this is potential due to the projectile charge felt by the electron, and the centrifugal force due to various, and because L is equal to 0, it is just wave, but then it is particle. So that gives you, because using the Levinson's theorem, one gets phase shift change of pi occurs, each scattering phase change of pi occurs, and that's what gives you the oscillation. Next one. Yeah. So for example, this is the total scattering cross, total momentum transfer, that if initially this is SP, that is at lower Z is equal to 5, it is SP, and then PD and DF. PD and DF. That is scattering eta 0 minus eta 1, eta 1 minus eta 2, eta 2 minus eta 3. Eta 0 minus eta 1 is this SP, and then eta 2, this is the PD and DF. Next one. Same thing happens here. So, but as you increase the value of K energy, then what happens is that instead of this, the effect of K becomes important. Can you go to the previous slide, please? Yes, the previous slide. Okay, just another previous little bit back, one more back. Okay, next one. Okay, here. So in that we will now talk about the unsaturated interaction, whether feedback is scattering and that. Next one. Yeah, so when you are changing, when you want to ion beam analysis in this side and ion beam modification is happening this side. For example, when you send ion beam, then some of the particles are going inside and this is the feedback is scattering and X-ray yield and all that, and it is what is happening in the other side of the transmission. So that is why ion beam modification is happening this and ion beam analysis is happening this. Next one. Yeah. So everybody knows that the feedback is scattering. That depends on the here the particle is coming and then it is scattered from the target, and then what you see it, you find out what is happening in detector. So ion beam, for example, proton or alpha is coming here, 3 MeV proton is coming, alpha particle is coming here, and then scattered, and then the scattered material, scattered particle, scattered thing, let's say information. But here it has to be either proton or a light ion beam. Okay. And next one is the elastic. Here, what is happening is the ion beam is coming, this heavier ion beam, and then it is scattered, and then it gives the it requires the target material, target M1, M2 that requires, and requiring is, and that gives you information. So the RBS and ELDA are the complementary thing. RBS gives you the information, the particle goes and that itself gives you information. Whereas in ELDA, the information is given by the required material, required of M1 and M2 from the target. Next. Next. So to understand the material, let's talk about gallium arsenide type direct band gap, and silicon is an indirect band gap material. Direct band gallium arsenide is direct band gap material, so that's why here you can see that conduction band. Here minimum conduction band is not exactly at the top of the valence band here, but here it is. So in gallium arsenide, it is gallium arsenide, it is silicon. In direct band gap, it is direct band gap. And that's why in gallium arsenide we can do much more. Next one, 3,5 compounds, gallium arsenide, gallium nitride, and all those. Next one. So here you can see that energy band gap as a function of the constitutional material. Gallium arsenide is here. Gallium arsenide. So in gallium arsenide, you put some indium, and it comes here. And indium arsenide, you put some gallium, it comes here. So one material is indium phosphide. Below that, exactly same composition, but the energy band gaps are different. Next one. Next. Yeah. So you have silicon, for example, gallium arsenide substrate. On that you can deposit either indium gallium arsenide or this aluminum gallium arsenide. Okay, indium gallium arsenide or aluminum gallium arsenide. So in each case, small number of layers. If you put very small number of layers, then they will not be adjusting to the substrate. Lattice parameter is different here, and that's why there is a strain produced, because you can see the strain introduced, but it has to adjust itself to the substrate. Next one. But if it becomes too thick, then here it is a strain material. When your number of layers is tensile or compressive strain is small number of materials, small number of layers, but if the deposit number are very large, then it does not strain, but the dislocations take place. Okay, let's say dislocations for the strain takes place at a small thickness of the epilayer, whereas if the epilayer is thick, then you get a dislocation. So both of these can be studied by the channeling. Next one. For example, here. So when you do the RBS scattering, RBS channeling experiment, then In this case, the 110 was 110 material, that is any helical direction, that gives strain, and that strain is reflected in the heat. Next one. Here. For example, there are two layers here. This is one and this is another one. And the gallium arsenide or gallium arsenide is even alternate layers. And when you do the back scattering, then you get the strain. Next one. Here. So if there are many number of layers, then you can have the some kind of resonance scattering can take place. Next one. Okay, next one. Next. So these locations will have different type of geometries and the strain. This has some area has only the lot of dislocation, lot of structure take place. Others are next one. So back scattering due to the dislocation affected channel will be different. Then the energy dependence will be different. Here energy dependence is a square root E type. Next one. Yeah. So quantum confinement, for example, these are these you have gallium arsenide and indium gallium arsenide or aluminum gallium arsenide. So this is the middle one, and then on the other side, suppose there is a this is gallium arsenide and indium gallium. So there is a gap, energy band gap, and then electron here, for example, this will not be able to go because the energy band gap has changed. I showed you in the second slide. Energy band gap depends on the material. So energy band gap, both sides is different energy band gap, and that's why it will be confined into this, and that confinement takes place because then that gives rise to energy levels are discretized, and then we get the radiation. Next one. Next one. So
sorry to interrupt you, sir.
No,
I think you should wind up as soon as possible because our technical session is already started.
So well, okay. So then I'm rushing through. Well, I will finish in next 5 minutes then.
Yes, sir. Sure.
Okay. So here it is the example of the two thickness blue two layers. Heterostructure T is equal to this. So this, if thickness of the layer is small, then it is one kind of physics, and if it is large, then it is next one. For example, this is when there are dislocation, then the dechanneling is square root E type, whereas the stacking fault is E to the 0. And when the point defect, it is like that. So the energy dependence showed you what kind of defects are there. Dechanneling by defect. Next one. Yeah. And then if you irradiate them, then compressive strain and tensile strain, for example, thinner layers, you have 12 to 36 nanometers. Then this is and after irradiation, the strain is increasing here. You can see that. But if it is thick, then it is decreasing. Okay. Strain increases because of when it is a small thinner layer, it decreases when it is thicker layer. Next one. The same thing comes with TEM, and next one. TEM results show that stacking faults are observed in micro of 60. So next one observation. Next one. So for thin heterostructure in the result in reduced defective density increase strain upon irradiation irrespective of the results obtained. Next one. So then if there are many layers, that is the 15 periods of this, then what you get is indium phosphide and indium gallium arsenide, indium phosphide, multi-quantum belts. Many layers are there. Here it is 15 layers. And then if you irradiate them, then what happens? It's a very, very interesting effect. Next one. So there is a comparison between that fluence of this silver ions and gold ions. Silver ions have more of less stopping power. Gold ions have more stopping power. Next one. Yeah. Energy loss decides that how much the radiation it will affect the change of the. For example, irradiated with silicon and irradiated with gold and silver. Next one. So compressive strain is induced in gallium layer by dynamic release. Next one. This is the same thing has been shown in the STM. Next one. Then one talks about germanium. For example, what I just now showed is the layers of the going from one to the other layers, interlayer strength, change of strength. In the case of germanium, next one, producing germanium nanoparticles. Next one, yeah. What one does is that synthesis of germanium nanoparticles are atom beam sputtering and ion implantation. These are the two methods by germanium nanoparticles can be created. So by annealing 700 to annealing with temperature effect, and then other is the doing the irradiation by the with the influences of the difference between annealing by temperature and annealing by this thing is that this can be special. You can have some at one place something else. It is special property is most important in the case of ion beam. Next one. Next one. Next. Okay, next one. Next. Yeah. So RBS of 2 maybe helium protons, 2 maybe helium ions is the detection analysis. And next one. Next. 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 Okay, so you can see that creation of germanium here, this is important that as you go to the higher and higher fluence, then the size of the germanium nanoparticles is increasing. This is most important slide of this part, that is as you increase the fluence, then the size of the nanoparticle is increasing. For example, fluence is increasing, fluence number of atom, number of radiation is increasing, then the size of nanoparticle germanium is increasing. Okay. So as a function of fluence, the size of nanoparticles created is increasing. Next one. Next. Again, next. Next one. So there are other processes, other, these are the atom beam splitting. Now we go to ion implantation. Same thing is done here. Ion implantation also the same process. Next one. Here again, you make the germinal nanoparticles. Next one. So this is germinal nanoparticle created on the silica, and then next one. Again, next one. Here. Again, when you increase the fluence, then again the similar results are shown here. Germinal by atom beam sputtering or unimplanted. Both cases, the size of the nanoparticle increase as you increase the fluence. Okay, more number of silver nanoparticles are going, then this is increasing. Okay, then this you remember. Next one. Go to next one. Next one. So here one is making the nanoparticles by the thermal process, and then radiation is earlier it was doing by ion implantation, and ion beam scattering was doing the nanoparticle creation. Next one. Yeah, so this contrast. See, earlier as a function of fluence, size of nanoparticle was increasing, now it is decreasing. And reason is, this is most important thing to understand in this talk, that as you increase the fluence, then when the nanoparticles are created by the ion beams, then it is increasing. But if you already created nanoparticles by thermal process, then you send the shift heavy ions, then it is opposite. It reduces. Radiation average size is reducing because the radiation fluence is going electron maybe silver ion. So that is, if the nanoparticles are created by ion radiation, then it will increase because more and more will be deposited. But if it's already created nanoparticles by thermal process, and then you send the radiation, then it is opposite because it is created. This is important thing to realize. It is as a function of fluence. Average size of nanoparticle here is decreasing because of the from the surface of the nanoparticle, it is going away. Particles are going away. Next one. So these are the other things. I think I would like to go to the. I think there are only 5 minutes are left. So you go to that last 4 slides. Keep on changing, and I will tell you where to stop. Keep on changing. I want to show the last 4 slides. Hello, can you change the slide to last 4-1? Hello, Manjeet. Go to last 4 slides. Go. Keep on changing. Same thing what I have showed, what I have told just now. Same thing is same here that if you the germ nanoparticle crystal size is decreasing when you are already existing, a radiation decreases that. That is you are depositing by the nanoparticles, it is increasing. Next one. Next. Quickly go to the last 4 slides. Decrease of radiation influence as we have observed a decrease in the average size. Again, this is because of the already existing nanoparticles, they are decreasing because the atoms are taking away from the surface of the material. Then we go to the next one. Go to the last 4 slides. These are something is shown by the TM. Keep on changing quickly. TM of the what I have said just now. Go on, keep on changing quickly. This is why the crystallization of the next one. Same thing. Yeah, all the results are similar in this case. I will not go to details of this. Same procedure is that if the particles are being deposited by the shift of the ions, then it increases the fluence, and if they are already there, then they decrease in increase of fluence. The next one. Okay, so next one I have said this just now. I have already told all this. Next one. Synthesized hafnium oxide. Hafnium oxide is instead of silicon oxide. If you go to hafnium oxide, show the next slide. Here, because if you here you have, for example, the energy versus the dielectric constant band gap. So as you increase the dielectric constant, this silica and this hafnium oxide is titanium oxide. So in this along this using silica, silicon oxide or hafnium oxide or titanium oxide has change of dielectric constant, and that dielectric constant is appearing here. Next one. See this process. This is what decides what you want to the dielectric constant K and A, area and D. There is a limit to which you can decrease D, and there is a limit to which you can increase A. Okay, but C can be controlled by dielectric constant. Dielectric constant of silicon oxide is much less. Hafnium oxide is much less. So if you can, once you have reached the limit of A and D, then you can go to the change of dielectric constant from silicon oxide to hafnium oxide, and that's why hafnium oxide is used for most of the present purposes. Go to the next one. Yeah. So instead of silica, then hafnium oxide is used for embedding the germanium nanocrystals. So hafnium oxide and germanium nanocrystals are being used because these are much better dielectric constant. Next one. The role of dielectric constant is important in this study. Next one. Here again, something RTA, do the RTA, and then go to the germanium nanocrystal is going decreasing, and then here you can see that. Next one. So the size of nanocrystal increases with the annealing temperature. Next one. Why it is taking so much time to change the slides? Go to the last 4 slides, as I said. You want to save time. You just remove, just bypass them. Go to last 4 slides. I want to take 2 minutes to discuss the last 4 slides. Go, skip all this. Go to the end. Can you not go to the end, last slide and last 4 slides before that? Keep on going. These are lasers. Then go to keep on going. Yeah, here. Just stop that. Go back to slide. That is what I want to say. Take 1 minute to discuss. One more back. Go back one slide. Yes. Vertically aligned silicon nanowires. First, what electrolysis etching is used to make the vertically aligned nanowires, and on that you put on some silver thing. Okay. So silver plus on vertical aligned nanowire, that gives you for the CRS. CRS procedure. Next one. Yeah. So to do because the surface is most important. So what does many nanowires are made silicon, and on that you dip into silver material and the silver nanoparticle deposit on silicon nanowires. That gives order of magnitude higher accuracy of determination. Accuracy of determination is at least 2 orders of magnitude. Next one. Next. Yeah. You can see that this is silicon wafer and silicon nanowires. On that one has deposited the silicon nanowires and the silver nanoparticles have been deposited. That gives the accuracy of determination of the material or CRS is that it becomes very high accuracy. The next one. I am quite surprised why it is taking so much time. So the molecular traces can be in explosive material. So the going to the one from one side to the other one, it is here it is showing me that order of magnitude small explosive can be determined by the this thing. Next one. That's all. I think that's the end of last slide. Yeah. So let me summarize in oral saying that there are two things. One is that when you are having you want to make the nanoparticles by laser ablation or by the heavy ion radiation, then as you increase the fluence, the size of the material increases. But when you want to, we are already having, then if you irradiate, then the size of material, the size of nanoparticles decrease because of the atoms are taking away from the. And here, what I was showing was that to have the detection possibility, detection of the small explosive is very order of magnitude increase by putting some silver nanoparticles on this silicon nanowires. Okay, thank you.